Well, I hope you had a great weekend. And we're going to continue with our monoprotic acids and bases and their pHs. Last time we discussed the definition of acids and bases, the autoionization of water, and the definition was according to Irenaeus, Bronsted, and Lewis. And we said we're mainly going to concentrate on the Bronsted, where the acid is the proton donor and the base is the proton acceptor. We then looked at the meaning of strong acids and their meaning relative to what we mean by a weak acid. We said a strong acid dissociates completely, while a weak one does not dissociate completely. We also then calculated the pH. We looked at the meaning of pH, and we calculated the pH of strong acids and the pH of strong bases, where their concentration is sufficient such that we can ignore the autoionization of water, and we'll get back to this autoionization of water equation plus the strong acids later on. We also looked at the strength of weak acids and weak bases, and we defined them by a pKa or a pKb and their Ka and their respective Kb values. And we said that the stronger the acid, the higher its pKa, and thus the higher the Ka, thus the lower its pKa. The stronger the base, the higher its Kb, and the lower its the pKb value would be. Of course, sometimes we see bases in terms of pKa's, and we can do such calculation. Remember, Ka times Kw, Ka times Kb is Kw, and let's try to remember pKa plus pKb is equal to 14, and you already did that application, and I'm hoping that you have completed parts 1.1 to 1.4 successfully. And I really want to tell you guys, you must, and I really must say this, you must take things one step at a time. At some point, we're just going to mix acids and bases, and you're not going to be sure, is it strong, is it weak? So one at a time, and make sure you swallow each one directly before we get into the next step, okay? Today, this chapter will be about the pH of weak acids. We're going to look at the pH again with no autoionization of water, and where the concentration is sufficient for that acid. We're also going to look at the ionization and concentration effect. Well, the best way to look at this is direct example, and this is a generalized form of an acid, which is weak. Thus, we can only calculate the respective amount of H plus from the equilibrium constant because it's a reversible reaction. It does not go completely. And if we're asked to calculate the H plus, the pH, and the percent ionization, this is what we have to do. We should set up what is called an ICE table. And this would be the initial concentration of the acid in the solution. So whatever you have in the solution, after dilution, of course, if you have a mixture, but overall, this is in a solution, you get its concentration of water because it's not a mixture. Here we have the initial concentration of H plus and the initial concentration of A minus are both respectively 0. It change. Some amount will react, some amount of H plus will be produced, and some amount of A minus will be produced. And at equilibrium, initial minus reacted, and X and plus X. All right. Now we have that underlined. Okay, so we said we have to solve for X to get the H plus concentration. And how do we do that? Well, you all know that the Ka is the products divided by the reaction for this Ka equilibrium. The products would be H3O plus times A minus divided by HA, where the water concentration is constant and thus we never include it, neither in the table nor in the Ka equation. It's actually already been included. All right. So what's H plus? It's X. What is A minus? It's also X. So we get X squared divided by HA at equilibrium. Okay, so we have it at equilibrium. So here's my HA at equilibrium. Initial minus the amount reacted, which is X. Great. Now what do? Oh, well, we can solve this quadratic equation because if I multiply through, I get a quadratic. Or we have an approximation, which is, and this is I like this approximation. It says if X is negligible, well, that doesn't mean that I remove this X. No, guys. Negligible relative to the initial amount of acid that I have in the solution. Negligible does not mean that this X is almost zero. Well, most Kas are fairly small, and X is negligible, but it's negligible here, not up here, okay? And thus, if that's the case, look at how much easier my reaction becomes. It becomes a lot more simplified. It just becomes Ka times HA initial, that's that, and that's going to be X squared, and then X will be the square root of Ka times HA initial. What is X? Well, it's simply the H plus concentration. Oh, that's nice. So I have the H plus concentration in solution. Once I have the H plus, of course, the rest is easy. Now I want to point something out here, and it's very, very important. Okay? What do I want to point out? I want to point out the fact that Ka for all weak acids is always less than 1. Okay? The strongest of those weak acids is HSO4 minus, and its Ka value is something to the lines of 10 to the minus 2. But still, the reaction proceeds, in the forward direction. And I get some X value here. I have the X. Now, the question is, how is that? Well, because the fact that Ka has nothing to do with the direction, and this is a question that you guys all ask me all the time. How is this proceeding, but the Ka, is a small number? Well, I'll tell you why. Because it proceeding in the forward or the backward direction has nothing to do with the value of Ka. Remember, if a reaction proceeds forward, it's the fact that Q is less than K. Okay, you have to compare the Q to the K. Okay, it has nothing to do with the value of K itself. What is Q in this case? Initially, if I start off with only HA, well, Q would be the products divided by the reactants at initial. Well, if the product is 0, then Q would be 0, okay? Well, this is too big here. So Q would be 0. Okay, so what do I have to do? If Q is 0, of course, no matter how small K is, it's still larger than 0. Okay, so Q is less than K. Okay, so if Q is less than K, the reaction will proceed. Of course, it will proceed only a very small amount because K is small. Okay, it doesn't have to go too much forward to achieve K. Okay, so that's a big time question for you, and it must be understood by you. Okay. Now, when is this approximation valid? When am I allowed to remove this X in the denominator? When is X negligible, in other words? Okay, so when is X negligible? It's only negligible when the HA, the initial concentration of acid, is greater than or equal to 100 Ka. So unlike the acid base, the strong, it's not a number that dictates it's actually, you know, a relationship between initial concentration and Ka. Now, there are some textbooks and some people that simply neglect X and say, oh, I'm just going to assume X is negligible. Okay, so that they assume that X is negligible, and once they assume it, they try to test it afterwards, and they say, is it really negligible? And in some textbooks, you see that it's negligible if the X is less than 10% of this, which is something that we defined at the beginning. As I said, if a certain material or a certain compound is negligible relative to another compound, it has to be 1/10 of it or 10 times less. So there are some textbooks that put it like that. There are other textbooks that say that it's less than 5%. And we're going to tell you only one thing, is that as long as C0 is greater than 100 Ka at the beginning of the equation, you could do that. Or you can test it out at the end of the Let me first do this. Okay. So now here, if X is negligible, okay, in other words, if C0 is greater than or equal to 100 Ka, we multiply the 100 Ka times that. We multiply the Ka times 100, which is we could do it in our head, so that we don't really need a calculator for this. And then you would say, okay, I assume X is negligible because this is okay. And if this is okay, then I could proceed. I could have the fact that Ka times HA is X squared, and then the H plus, which is the X, is simply the square root of Ka times HA initial. I can go further slightly with a nicer equation than this. Of course, this is always easy to apply. Most textbooks apply this type of an equation, but you know, we have even something easier here at the Lebanese University, which does the following. If we take minus log of both sides of this equation, okay, take the minus log. Take the minus log of this, okay, of both sides. So this would be minus log of H plus equals, the square root comes down in front of the minus log, and then the minus log goes inside of here. Minus log of a multiplication is the minus log of the addition of them. So minus log of Ka minus the log of C0. C0 again is the initial concentration of that acid. Great. Now, what's minus log of H plus? It's simply the pH. What is this? Minus log of Ka, oh, that's pKa. Okay, so if I give you pKa, well, what you can do is just simply apply this equation, because you have the pK. If I give you Ka, well, I don't know, you could do either or, but you could also go ahead, find the pKa. Well, if you have the Ka, say it's minus log of the Ka, and get a number here. Okay, let's continue with this. I'm taking the half to the inside, so this is also minus half log C0. Of course, C0 is the concentration of the acid in the solution. Great, and this is all you're going to need. That's it. If I have a weak acid and I want the pH, okay, I would say the pH equals half pKa minus half log C0. And that's in the majority of cases, because the majority of cases have the initial concentration greater than 100 Ka. We will talk about some other cases, but this is the majority of the cases. Let's do a direct application, shall we? What is the pH and the percent ionization? Oh, did I do the percent ionization here? Okay. Well, we'll do it right now. What is the pH and the percent ionization of 0.5 molar HF solution at 25 degrees Celsius? Remember, Kw is 25 degrees. Okay, so here I have HF. Of course, it's reacting in aqueous water solution, so there's plus water here. And I didn't need that. And then we have H plus becoming HF. Okay, what is the Ka? It's the products divided by reactants. Fairly clear now. I'm not going to put it what it is. And the number, you have it right here. It's something 10 to the minus 4. Ooh, isn't that negligible? Isn't that non-reactive? Isn't that, does not necessarily proceed or practically proceed? Well, yes, in cases where, you don't have an initial concentration on the product side, which is 0, okay? Because my product is 0. Again, Q is 0. So no matter how small this number is, no matter how tiny this Ka value is, this Ka is still greater than Q, okay? Or Q is less than the Ka. So the reaction will proceed, guys. Minutely, but will proceed. Okay, so we have initial concentration, and of course you all now know this, minus x plus x plus x, and initial minus x, x, and x, okay? All nice and dandy, my ice table initial change equilibrium has been established, and we do Ka. Ka is going to be products divided by reactants, or H plus times F minus divided by HF, which is x squared initial minus x. This should be like, bang. You don't really have to every time put this ice table, to be honest with you, especially if it's just a weak acid on its own in water. Right away, you could say Ka is x squared initial minus x. You could even apply the other equation immediately. But we're going to do this for now. Again, I'm doing it the long way, and then later on you're just going to see me just applying the other equation, which gives me the pH immediately. But initially I want you to go do it the long way. Of course, if C0 is 100 times greater than Ka, so let's test this. If I multiply by 100, this becomes 10 to the minus 2. So that's gone. This becomes minus 2. Oh boy, okay. This becomes 10 to the minus 2. And, well, this number, 0.5, is still bigger than 0.007. So this is okay, dandy. Great. Check mark. And thus, this bottom part, the denominator here, becomes approximately simply 0.5, as if and we simplify and we get the x is gone from this equation. We get this new one and we solve for x squared. X squared is simply Ka times 0.5, which gives me this number, and we get x equals 0.19. Now at home, guys, I really want you to pause at this point. And from here on, I want you to have a piece of paper and a pen and a calculator. Because you really have to start practicing these, minor reactions, or, not very hard problems, because eventually they will get harder, okay? So get to know them by now. So if I found x, that means I simply found the H plus, yes, and the F minus. There you go. And that's my x. If I have my H plus, of course, I have my pH. pH is simply minus log of H plus, which is, plug in the numbers and you get pH is 1.72. Oh yes, it's an acid. Yes, it's a weak acid. But remember, weak acid has nothing to do with the acidity. This is actually quite acidic. Okay, it's a weak acid, but it's an acidic solution. Okay, because it's quite a high concentration actually. I could also find HF if I'm asked for it. It's the initial minus x. Oh, but I thought this x was negligible. Wow. Turns out that actually HF is 0.5 minus x. It's negligible in calculation of the x, because if you didn't consider it negligible, this would very slightly and I could go ahead and not consider it negligible, and I would find the exact value. But overall, it doesn't make that much of a difference to the pH. Percent ionization. Amount ionized. Okay, so that's the amount that comes out as the ion form. So that's actually the X, okay, which is still H plus or A minus. And so that's the X divided by the initial amount. So how much ionized is the ratio of X divided by initial times 100? And we get that the percent ionized is 3.8. This fits into the English type of examples. What they do is, in English textbooks, they don't look at this C0 times 100. They actually assume X is negligible, and then they always have to find the percent ionization. And as long as it's less than 5% in most textbooks, you know, they say that you can neglect X. And again, when can this approximation be used? We always use it in this course whenever C0, or initial concentration of acid, is greater than 100 Ka, and you check this right before. We will also check it right after. Some people assume it's negligible, and we're going to see this in some of the exam textbooks. Then we check, we see that the pH is less than pKa minus 1. Again, where did these guys come from? We're going to look at this at the end. I'm going to derive for you where did I get this and where did I get that. But I don't want you to worry about that now. I want you to worry about the actual calculations, okay? That's my 5% rule there. Always, it's always faster, right away. Whenever we can neglect autoionization of water, C0 is greater than 100 Ka, and you say pH is a half pKa minus half log C0, and the percent ionization can also be found directly. Remember, if I want the H plus concentration, I can get it from the pH, right? H plus concentration is 10 to the minus pH, and that's the X. So 10 to the minus pH, that's X, divided by C0 times 100 is my percent ionization. Okay, now, go ahead, try to solve the same question that we just did, only applying this equation. And that's what I did here. I'm not going to go through it. You try it, apply this equation, and you would get the same exact pH and the same exact percent ionization. I love actually this equation. I never learned it when I was an undergraduate student. That's too bad. It would have really saved me a lot of time. I don't have to think. Use it, guys. As well, if you check at the end of the pH that pH is less than pKa minus 1, you can also check that. Now, let's look at the same question. What's the pH of HF? Only this time, instead of 0.5 molar, it's 0.05 molar. The question is, why should it vary? Is the type of equation, do I have to do something else to the, ice table? What is it that I have to do? It turns out that this C0 is less than 100 Ka, greater than 100 Ka, remember that? Well, in this case, C0 is not greater than 100 Ka, because multiply 100 by this becomes 0.07. Well, 0.071 is greater than 0.05, or 0.05 is less than this number. So I can no longer neglect this X on the bottom. If I did, let's say I did, and I continued on, I neglected the X, and I then solved for the X here. Again, this is my new concentration, 0.05. And I continued, solved for the X. My X becomes 0.006. And then I got the percent ionization, whoops, 12%. Oh no, that's too much, okay? I'm not allowed. That's, at least that's too much for this concentration. Not that it does, but this acid has a percent ionization that's quite high, okay? And thus, we go back to the ice table. The ice table doesn't change, guys. For a weak acid, I still have the same ice table. It's still, I'm gonna go back on purpose here. Bear with me. Okay, it's still the same as this. It's HF goes plus water, becomes H3O plus F minus. Remember, H3O plus, or I just sometimes put H plus for simplicity. Except here, the initial concentration would be 0.05, okay? This doesn't want to write anymore. 0.05, okay? That's the only difference. But you still do the same thing. Now, again, you will never on an exam have to write this table. It's always x squared divided by initial concentration minus x. Again, we're talking about simple weak acids in water. Okay. Now, so the ice table doesn't change. So here's my x squared initial minus x equals Ka. And am I allowed to neglect x? The answer is no. You're not allowed to neglect x. So what do you have to do? Okay. You have to multiply everything through. So you Ka times 0.05 minus Ka times x. This would be on this side. Then take everything to one side of the equation. And you get, voila, a quadratic equation. It's of the form ax squared plus bx plus c. And of course, you could do it the long way, and you solve for x, and you put x equals minus b plus or minus square root of b squared minus 4ac divided by 2a, but you'd be a retard to do that. And of course, you're not retarded. What do? You use a calculator, guys, okay? You have to learn. Use your calculator. Learn how to solve equations by the calculator. If you don't know how to do that, go and learn, okay? Of course, in the calculator, it gives you two solutions, an x that is positive, an x that's negative, and of course, x cannot be a negative solution, okay? I'm just reminding you of here, of the ice table, that's where I got this from and whatnot. So once I have my x is simply my H plus concentration, and I get my pH, okay, minus log of H plus. So pH for weak acids, where the concentration C0 is not greater than 100 Ka, so it's less than 100 Ka, do is use Ka equals x squared divided by C0 minus x and get the quadratic, okay? Now, you could sit there and memorize this, that the quadratic equation is going to be x squared plus Ka times initial concentration. I don't like to memorize, so I just go back to the original x squared divided by C0 minus x. But you do sometimes save time by memorizing. Even better equation to memorize. This is the same thing, this just using HA as a general. So Ka, again, reminder, is H3O plus times A minus divided by HA, which equals, remember that A minus is equal to the H3O plus, so this is going to be H3O plus squared C minus H3O plus. Well, that's retarded, but okay, that's fine. Now, you multiply out with the Ka is times the C, Ka times the H3O plus, and here's the H3O plus squared. Take everything to one side, and you get this. So this is what you see and what you will, if you want to memorize, go ahead. I personally just go back to this and solve it. Okay, so this is an example of my HF using this equation immediately. Okay, so if I have C0 is less than 100 Ka in this example, 0.05 is less than 0.07, then I simply use this equation, okay, use that equation, which is, if you want, h plus squared plus the Ka value, whatever it is, times the h plus minus the Ka value again times the initial concentration. Don't forget this minus here. A lot of you forget it. It's plus the first one, and the second one is a minus charge, okay? I always forget it when I apply it. Even here, sometimes I forget it, and I make a mistake on the calculator, and you should not do that. So use your calculator. Of course, the A is 1 here, as it usually is. And the B would be your Ka value, and the C would be minus Ka times C0. Okay. Solve for that. Try it on the calculator. Do yourself a favor. You must do this. Under no circumstances you should do this before we continue on to the next movie, or yeah, it's like a movie, next recording. You must, and I really say you must, try it on a piece of paper and a